Great. So Salsabila has done the work on vegetation and cool materials on developing envelopes, so impacts in indoor temperatures and energy use in Indonesian tropical residential buildings. And this has been done under the MSc of Built Environment, Environmental Design and Engineering. So Salsabila, when you're ready, you can start. Thank you.
Okay, thank you very much for the opportunity. As mentioned earlier, I'm studying the impacts of the use of vegetation and the integration of vegetation and cool materials on building envelopes to the indoor temperature and energy use in residential buildings in Indonesian tropical climates. And as a background, obviously, we all know that as the climate change happens, it's resulting in rising temperature and frequent extreme heat events, and also the UHI effects exacerbating indoor overheating and thermal discomfort within buildings. And in this context, Indonesia, as a developing country in the tropical climate, which is exposed to prolonged sunny days, also have an extensive exposure to the solar radiation, is very vulnerable to the overheating. So that, as we all know, that building has a very huge contribution to the energy consumption. It is essential for building to contribute to mitigate by reducing indoor temperature and cooling energy use. And as my focus here, I'm using the East Kalimantan weather file as my case study, because Indonesia is currently relocate our capital city to East Kalimantan from Jakarta, which actually East Kalimantan is located in the equator zone, so that it has much more exposure to the solar radiation, and it also has longer sunny days within a year. And actually, the government is trying to reduce the environmental impacts to the current Kalimantan's environment, while actually the current Kalimantan's environment is covered by forest. But the government is showing their sustainable approach, one of which is by implementing some biophilic and biomimicry approach in its building by integrating green roofs and vertical gardens in its envelope. So the roofs and the walls are tried to be covered by vegetation. And after literature reviews done by me, I found that not only green approach, but also cool approach, which is widely known as the use of cool materials. Cool materials is defined by the use of low albedo materials in its roofs. Both green roofs and cool roofs is identified as an effective solution to reduce internal heat loss. And so that I am interested to learn how does the impact of vegetation and cool materials elements into roofs and walls in buildings within the Indonesian tropical climate settings. So this is the location of the East Kalimantan itself. And the methodology of this study is I use 3 different kinds of building as my object to try to figure out how does the implementation impact within different building complexities of residential buildings. The first one is a single detached house, and the second one is a low-rise vertical housing, which have three stories. But I tried to analyze the difference between 3 units within different levels. And also the third one is a mid-rise vertical housing with 8 story. And I analyze the units in the ground floor, the 3rd floor, and the 7th floor to have the representatives or building in lower, middle, and upper floor how does that impacts the indoor temperature within those units. And the methodology is pretty straightforward. I tried to build a model within using the base case, construction materials, internal gains, and also the building geometry. And I have 5 different kinds of iteration scenarios with which I changed construction materials to implement the vegetation and cool materials in its roofs and its walls. The first I simulate it using the current weather file, and I run another simulation using the future weather file to see the long-term potential of energy reduction from the use of green roofs, green wall, and cool walls. And to show you guys, so this is the settings that I use for the base case construction materials, which can also be seen that the building has different kinds of roofing materials, which also will have an impact on the indoor temperature because of the different number of U values, which have strongly related to the indoor temperature itself. And for the iteration scenario, as I mentioned before, I do 5 different kinds of iteration scenario. So for the base case, I use the base case construction material. For the green roof, I only focuses on the extensive green roofs, which have lower impacts to the structure of the building, because Indonesia is very vulnerable to natural disaster. And for the green walls, I only focuses on indirect green facade. And also for the cool roofs and the cool walls, I assume that I use a low albedo materials for the roofs and the walls of 0.8. So the cool materials tends to have lower solar reflectance, which makes it reflect most of solar radiation that coming into the building envelopes. And the idea why I concerned about the roof and the walls, because I tried to find how that a building that have more stories and dominates by walls, external walls, how does the change in walls material affect the indoor temperature? And these are the scenarios that I've done. Not only just 5 scenarios, I also try to simulate the building using different pitch angle, and also in the roof I tried to use insulated and uninsulated scenarios, which the insulated ones is have another layers using double-sided aluminum foil insulation, which is very common in Indonesia. And as a result of this study, I found that a green and cool building envelope can reduce indoor temperature in East Kalimantan by an average of less than 1 degree Celsius, which is compared to previous study is relatively low. However, I found that roof adaptation yielded more substantial cooling benefits than wall adaptations in 3 case studies I have. Which is can lowering the indoor temperature below the roof by an average of 0.55 to 1.33 degrees Celsius. Why I said here lowering the indoor temperature below the roof? Because actually the impact of the changing of the roof adaptations to the lower stories is pretty low, so that it only affect the upper floor that is below the roof itself. And also the cool adaptations showed greater temperature reduction compared to the green. However, as can be seen in the graph, according to day and night temperature analysis, the cooling benefits of green roofs surpass those of cool roofs during peak temperatures with a substantial decline at night. So that it also aligned with the previous study that actually green roofs can provide more benefits during peak temperatures, but in Indonesia setting itself, cool adaptation during the day can provide more cooling benefits compared to the green adaptations. And also by adding reflective insulation layer, as I mentioned earlier, I use double-sided aluminum foil. To the green roofs and cool roofs, using metal materials provides an additional mitigation effect on radiation. However, for the concrete roof, due to its thickness, the effect of the double-sided aluminum foil itself obscured by the thickness of the concrete roofs. And in taller buildings, which I have 3 different complexity of building, have a greater potential for overheating compared to the lower ones. While a single houses and room on ground floors are highly likely to achieve thermal comfort. This might be also affected by the fact that I only covered the one areas of the walls within different kinds of unit in vertical housing, but that's one of the limitation of my study. And also on building with metal roofs, which is the single detached and the low-rise building, the high conductivity of the roofing materials cause more cooling benefit in daytime peak temperatures, both in green and cool. On the other hand, buildings have lower diurnal buildings with the concrete roofs have lower diurnal or daily temperature variations. And for the for the future impacts, the cooling energy savings achievable from the use of cool roofs decrease as climate change intensifies. However, it's still worth to try to change the construction materials of the building envelopes to reduce the indoor temperature. And as a
Great.
conclusion, thank you very much for the opportunity.
Thank you very much for the presentation and sharing with us this very interesting and slightly more technical topic. So, what do you think is the biggest challenge if you are working on a topic like this? I mean, it was very interesting to see how many scenarios you try to analyze and how many different aspects you try to simulate. But in terms of the challenge, what do you consider is the most significant one?
Yeah. So actually, the most challenging thing is I relied on the simulation itself for my results. So if I happens to find something that not reliable as my inputs, that will have something to do with the outputs I got. And actually, one of the challenge is because the simulation itself using very relied to the software package. Sometimes I found sometimes in license, so I got license issues back at the days and something like that. But actually, I got some helps from my supervisors about handling the problems with iteration scenarios and so on. So I think this is a very interesting journey, and I got a lot of things to compare. Although it's a very straightforward comparative study, I think doing many iterations makes me understand a lot more things. So I think this dissertation teach me many
Yeah.
things. Yeah.
Great.